this is the potential energy. This is the reaction path. And in this case, for an endothermic reaction, what I want to model right now is an endothermic reaction. The energy of the reactants is actually lower than the product. So we start down here for the reactants, and as you proceed through the chemical reaction, the products actually end up at a higher potential energy. So in this case, obviously, for this reaction to occur, there has to be an absorption of energy. So that's why they say energy is absorbed. And then the opposite for the exothermic reaction, which is what I accidentally drew the first time, is the products start off, the reactants start off at a higher energy level and end up through the course of the reaction at a lower potential energy level, the reaction path, increase in potential energy this way. And so if you start off at a higher energy for the reactants, then as you proceed through the reaction, through the path of the reaction, your products are going to end up at lower energy, and so in this case, energy must be given off to get from a higher place to a lower place. That's why they say energy is released. Okay, I just wanted to model it a different way because sometimes if you may have seen it this way in your pre-AP chemistry class. All right, it's just another way of modeling what we're saying here for an endothermic reaction and an exothermic reaction. All right, so right now we'd like to see if there's some kind of theoretical way to calculate this energy difference, whether its energy is absorbed or energy given off. We saw in the first part of the lecture, part 1, that you can use a calorimeter to experimentally calculate how much energy is given off, given the heat capacity of your calorimeter and your water. You just look at the change in temperature to calculate the heat given off. But where does that heat really come from? Well, if you remember this concept of bond energy, some bonds are stronger than other bonds. We can use the concept of bond energies to to do a theoretical calculation to predict what the heat of a reaction should be. Now, the bond energy is the amount of energy that must be absorbed to break a specific chemical bond. That's how bond energy is defined, as the amount of energy that must be absorbed to break. So if you've got a bond made, the only way to get it unmade is to add energy to it and break it. And then the converse is true when a bond is formed. If you have two individual atoms and they come together and the bond is formed, an equal amount of energy would be released. Okay, so if it takes, say, 100 kilojoules to break a bond let's say it takes 400 and some kilojoules to break an HH bond, hydrogen-hydrogen bond, so it takes around 400 kilojoules to break it. When those two atoms come together from some distance apart and come closer and closer and closer and form a bond, then energy is released. It would be the same amount of energy, about 400 kilojoules. Okay, so you'd have to put roughly 400 kilojoules in to break a mole of those bonds, and when you form those bonds, about 400 kilojoules of energy is released. Okay, so that's what they mean by an equal amount of energy is released. All right, so bond energy is a form of potential energy. It has to do with the potential of atoms and their relationship to each other. So it's chemical potential energy. So for example, when we talk about a fuel, say octane, say octane contains chemical energy, what we're talking about is the energy, the potential energy that's stored in its chemical bonds. Okay, so that's what chemical energy is, that's what potential energy is, and that's what bond energy is. All right, it's all relating to the same thing.